Okay. I have already installed the HEC-RAS software in my computer, so this is the icon. So to start, just click here. Then the first step is to create a new project. We can put the new project anywhere, but I have already prepared a folder for this Boaron 3. We can name them Boaron because the name of the river is Boaron and located at Morge, just it is near to Geneva. Okay, okay. The new project is already created, has been created. So the next step is to make sure that the unit system is always in the international metric or metric system. So just click here to make it a default system. So that's all. Then the third step will be to create or to add some data, geometrical characteristics of the river. Then next, the hydrological parameters, the discharge and so on. These are the data we are going to put. So click, then first we have to create a new geometrical data, then just name it geometry Boaron, geometry of Boaron. Okay, now the file is already created. Then click on river, just press the right click of the mouse, the right side of the mouse, just put it down, then double click, then this window will come, pop up out, and then name the river Boaron. Then the ridge is assume give a name DS ridge. Let me make this one copy, and also let me give this one 1 to avoid confusion later. The direction of the flow, the name of the river, and the name of the ridge is created. And next we have to put the data here, the cross-sectional data. To put the data we have to click here, add new cross-section, then you start from 1, then give a description, cross-section 1. Now let me show first the site. This is the site. The site, you see, has some forest covered areas. Let me, the green dotted is the green dots are all trees. It's a forested area, and there is an asphalted route. You see, there's an asphalted, very small but asphalted route, and there is also a new canal. They call it a didactic canal. I mean, that is for educational purpose, I think. Or, is going to be built here, but I think it's just simply a plan. It doesn't exist at the moment. And this one is the river. The cross section is here from 1 up to 14. Because the HEC-RAS process the data or calculate or start the calculation from the downstream side to the upstream side, we have to put the first cross section, this one, not this one. The other side of the river, this bank is also covered with some trees, but when you go a little far from the river, then it is a farmland. That's all, and the data is already given here. So these are the data. Profile number aval means downstream profile. The first, then you just copy and paste it. Apply data. That's all. That's it. An option and a cross section. Just 2 x2 number 2 number to make sure that here this is number 2. Copy. Control V, paste, apply. That's number 2. Option, the same procedure up to 14. Now X is 3. So it's not necessary to show all steps here. Okay, because it is a repetition, you see, not necessary. Up to 14 it is the same procedure. Apply data. This is the third, the fourth. Okay, X is 4. Okay, come 4. Apply data. Number 5. X5. Double 6. Data at cross section 7, 7. Eight. Apply that. Option add new section 9. Number 10. Apply data number 11. data 12 apply data 13 14 number profile number 14 among means upstream far end upstream far end. So this is the end. Now this is good time to save the geometric data. Now we have already placed all the cross sections. Now we need to put the distance between the cross sections and the manning value and the main canal bank stations. You see which one is the left, which one is the right bank, and which one is the central canal. We have to specify. Downstream reached length can be shown. You see, it means the length between the two cross sections. Cross section number 1, number 2 here, there is a space, and we assume that the distance between them, the left bank and the right bank and the center, is almost equal. That's an assumption. Also, there is very little distance differences that can be assumed equal, almost equal. So that is the length. And the downstream distance, from the Lake Lama to the first cross section is given 50 meter. This is the location of the Lake Lama. So let me go to the distance inter profiles. The distance between profiles, it means the first from 0 up to 1 is 15, then the next 17 and so on. Just we can copy this or copy and go to just exist this one and go to table reach length. You see, just click all, control paste, click all, control paste, click all, control paste, finished. You can see all the distances are now in. You see number 1, 8, distance between them 15 and so on. Now the manning n values. How can we put n values? The n values can be seen. Let me check. See, just you can see n means let's see that. You see, k strike is equal to 1 over n. So let us forget about what k striker means, but this is a formula, and these are just examples, the pictures, and the value of K-strike K is given. For example, for this artificial canal, lined canal, as K-strike is equal to 45, then 1 over 45 is n, that is inversely proportional. So 1 over, it means here n is very small number. The more the canal is smooth, then it will be, I mean, the roughness coefficient will be less, and roughness coefficient for this one is, K-strike for this one is 42, and so on. It's indicated like that. So our condition looks like this one. I mean, the river condition. I can show you the river, you see. Let me show you the river. This is the river. We can see it. We can see the river together, see. This is the river. This is the Lake Lama. And this is the end of the Boiron River. It's separated by a dike, you see. There's some kind of dike. They separated the river from the Lac Lemo, I think in French. So this is the entrance, the area by which we can access the bottom side. We can see the river condition from the bank conditions. You can see, just let me forward it. You see the bank, the two banks, left and right banks, covered by just the tree. You see there are trees, and the bank condition is okay. It's okay. I mean, it's just seems like an artificial canal, rectangular canal. It's okay. See, this is the situation. So it's good to see that helps us to visualize. So this is exactly our case. You see, there are forests and there are some stones actually, but the depth is different. Our river has more depth, or deeper than this one. So let us assume our K-strike is equal to 31, and there is a table here. Just our states, perfect state. It's a very good state. Actually, let us say bone. Eta de paro means the wall is okay or good. The state of the wall, it means that means bone means good. I say bone is a little bit less than good. You see, movies is bad. Therefore, let me consider this case. Then the strike will be, let us consider 30. The end value will be 0.033. You see, let us go and put 0.033, and the next step is to see if, for example, see when the trees, I mean, not actually densely like 3 something like that, but like it's just sparsely populated trees have K-strike equal to 20. I'm not sure which one is our condition, either this one or this one? Maybe let us consider case track as this one, because there are dense case track 10. Okay, let us take and see, for example, go and see 10. There is nothing actually. Okay, there is 10 here. So the end value for 10 would be 0.1. Zone avec beaucoup de mauvais service. This means a lot of bad herbs and so on, as 10 says. Zone coulant lentement avec herbs or for the trap. Maybe this is one. This one is you see, zone or coulant lentement means flows slowly. A zone of water that the water flows slowly. There are harbors and also the deep root trees, I think. It's a situation. Maybe this one, 15 maybe. Let me take the 0.06. 0.06 and both sides the same, 0.06. Okay, but to put all the, see, for each section assuming similar Manning values, we have to go to the exits from here and go to table, and it will be easier to put, you see. Let me copy, paste. I can just copy and paste like this. I'll paste like this and copy, paste like this, paste like this, paste, copy, so copy. That's it. Every cross section has already the n value in. And the next step is to put to specify which one is the left bank, which one is the right one. See, we can click here. Just let me show you again, just to show. Here you see, here's an icon here, button. Just click, and then the cross section comes. Then which one is the left bank? This one is the left bank, and this one is the right bank. See, proportional. Okay, this is for number 8. Let us go from 1 up to 14. This one and this one. This is number 1. Go to number 2. It's number 2. That is number 2. Number 3. We can make it bigger. So click. Okay. This is okay. Number 4. This is the bank actually, and this 5. As 6. Yeah, you see the n value adjusted by itself when we adjust This, you can see the red dot here. Those are the adjustables. 7. That is 7. Number 8. It's already, I have already done that on 9. Then 10. Yeah, that's the bank. Actually, some very different. It's wider here. The banks, you see, a little bit lower here. Okay, let me see. 11.1. That is okay. 12. This is flat, almost flat. As is. These are the banks. Okay, 12, 13. 14. Okay, that's all. Now this is a good time to save our geometry. And that save. You see, everything is now in geometry is almost finished. There is no other behavior, that parameters that we can add. The contraction and expansion, this coefficient is constant, I think so. It's okay. So this is all about the geometry, adding geometrical data to our model. So we are finished already. Then to add the hydrological data, we need to click okay. The geometry of Byron is already in. Now the hydrology of must be in so that we can run the model. You see, to put the hydrological information, just click the fourth icon, setting, because we have here 9 profiles. Then you see that says, and it also requires us the upstream and downstream conditions. What are the upstream and downstream? Downstream conditions is the elevation is known. It means I can show you here the elevation, the water level elevation. This is similar as we have seen. There is a dike, the river and the lake is almost equal, and the lake elevation is regularized always at 372.30. That is régulation du niveau de l'Emo par la barrage de Sougia à Genève. There is a dam around Genève. You see, it will be regulated by the dam. So the elevation is known, and it is 372.30. That is so 372.30. Copy. Okay, so that's the elevation is no elevation 70.3. And the upstream we can take as a critical depth. I just want to take as a critical because we can see from this video that the upstream side, you see the upstream side is the semi, I mean it's not actually critical, but it's almost critical, you see. So you see the flow here is it's a critical flow, for example, around this area. So let us assume it is a critical flow as the upstream section. A critical flow is a flow that has a flow number 1, subcritical is less than 1, supercritical is greater than 1, which means a flow that has a hydraulic jump. So that's it. Okay, and here we have to put the value of the discharge that for different return periods. First let us change this thing. Option profile name, the profile names, yes. Okay, click. The first will be Q347. It means this is the lowest flow, the driest. That is one return period 2.33. One return period is 5. That's 5 year. Let me make it like this. It's just simply it's just a name. So we can see. Let me click, copy, paste. Okay, and 5, that is 10, and that is 20, and that is 30, that is 50, that is 100, that is 300. That's just simply a return period. So the first return period is 0.5. So it's actually not the return period, meter cube per second. It's not a return period. This is just a dry period flow. T is equal to 2.33, 8.7 to discharge. At 5 returns period, 0.2, 10, 13.3, then 20, 15.3, 15.3, 16.4, 17.9, 13.3, 17.9, 19.8, and the 301 is 22.8. These are the written periods. I mean the discharge of the written phase, the value of 30, 300, 100, and so on. So we can save now file and save flow data. Okay, that's all. This is boron hydrology. That's all. We have done it now. Everything is done. The geometry bound boron hydrology is already in. What other data? We don't need any other data. We can run now. Just click just to a steady flow simulation. Leave it subcritical because river flow is always it is in subcritical unless there is hydraulic jump, something like that. So just to compute. This is the result. This computed. Okay, then just new plan, save plan. Actually, it's not okay. Just to run, we have to create a new plan. Call a new plan simulation boron. See simulation 1 boron. Yes, this is simulation 1 and short name sim1. That's all. Now compute. Yes, it's computed. Okay, then save the plan. Okay, you see the plan is the simulation is already in. Now just to see our result. This is the result. See, you can see, you can animate. You see this is for different return periods. This is for 300 at cross section 14. You can see this one. You can see number 8. You see some water already here. You can see it means there is a flooding here. You see. Number 6. Number 7. Oh, number 7 is also. You see there is a flooding here. Inundation. What about 9? It's almost, see. So that's it. We can see the longitudinal profile as well. Let me see the longitudinal profile. See, this is the longitudinal. You can see. Now these are the walls. Let us. We are concerned only for 100 years return period. Okay, I think see here and here and here the inundation. This is 100-year return period will flow over top here, over top here, and over top here. So we need to do something. We have to build, you see, a wall here, That's the recommendation. A wall, but it's not necessary to build a wall here because that is a retain wall, a protection wall, because it is almost the lake. So there is no need. There is no structure that will be inundated. So it's not necessary to build here, but we need to build here between this, you see, number 7 up to this, maybe up to 8, number 7 up to 8. It is around 188 from 140 to 188, therefore 46 meter, around 46 meter here, and also in this region, that is in section 12, between 11, 13, the 13, yeah. Let us check why this happened. I mean, around 13, you see, actually there is the banks, you see, yeah, there is the inner, this is the inner energy grid line. Around 12, see, it's almost always, there is not overtopping at 12, because okay, we have to look again the bank, you see, we have to see. Okay, so there is an error. There is an error. The second simulation, let's go and correct our error. 12, see, the 12, the red, the embankment is here. See, we have lowered the embankment. Okay, then we have to save geometric data, and we have to run again. That is number 9. We have to create another new plan, that is a simulation to boron. Simulation boron 2, okay. Sim 2. That's all. Copy, compute, close, save the plan. That's all. Now we can exist. Now we can see our data now. This is a profile. So let us see the, okay, it's okay. Now it's okay. There is no problem here. We see we have all this that is a problem. How many meters we have? Around from here 142 up to here, up to 188, 142, 188, 46 meter. Yeah, almost 45 something. Yes. See, we can animate. That's for 300 actually. Let us see 400. Yeah. That's 400, okay. That's 142. Around between number 7 and 10. Therefore, we need to build around, yeah, that's all. And also, the other is not important. We can have this one as copy into keyboard as results. We can copy it here. Yes. Paste. So this is 400 years. And these are the values, the results as well. So we can save our project and close. Save our project, then close. Merci beaucoup for listening.